righty, friends. So last class we talked about relative extrema and increasing, decreasing domains. And then we also looked at how this big idea of the first derivative test. We're going to use this first derivative test today in another setting, although it's not going to be for the first derivative. We're going to use that idea for essentially something called this on the second derivative. So we'll talk a little bit more about that here in a second. All right, so to begin with, remember, we talked about how on a function, we have some relative maxes and mins. But today we're going to talk about something else, and it's not necessarily tied to the first derivative. It's going to be tied to what we call the second derivative. You see, I want you to see if you can go with me here a little bit. Do you notice how it looks like there's a point where our graph kind of appears to go from being a rainbow to being a cup? Can I say that kind of goes from being a hill to being a valley? There's a point where it changes directions. Well, that point is called a point of inflection. It's where our graph kind of changes the opening. Does it open up or does it open down? All right, and that occurs, this can occur when our second derivative, not our first derivative this time, but our second derivative is equal to 0, or when our second derivative is undefined. That's when a point of inflection can occur. Doesn't mean it does, but it can occur. Is undefined. Well, these openings are called, in calculus, we call it concavity. So these openings right here, we'd say that this is opening down, and we have a different word. We don't call it opening, obviously. We say that this one right here, it looks like it's opening up. Now, if it's opening down, we say that means it is concave down. Concavity means opening. So concavity, instead of opening up, we say concave up. Instead of opening down, we say concave down. So this is concave down. This is what the concavity looks like. This concavity right here, since it opens up, we'd say it is concave up. Now, anything where it's concave down, it's pointing towards negative infinity. So since it's pointing towards negative infinity, you kind of see it here a little bit. It's opening towards a negative infinity y value, right? Well, we say then that turns out that part right there has a second derivative that is less than 0. Likewise, if it's concave up, we say that it has a second derivative that's greater than 0. So a graph has a point of inflection when the second derivative changes signs, or the concavity of the graph changes. For instance, let me draw another one here for you. Again, let's have it go the opposite way here. So I'm going concave up, change, concave down. That point where it changes, we call that a point of inflection. So what we end up doing today is something very similar to what we did last time. We're going to do this kind of test the derivatives and make sure that it changes. However, please realize that it doesn't really matter for us how it changes. No, for relative extrema, we had two different types, relative max and relative min. So we had to talk about how it changed. Did it go from a positive derivative to a negative derivative? So it was a relative max. Or a negative derivative to a positive derivative, so it was a relative min. Or what we're doing here with points of inflection, we don't care. All we care about is did it change? Did the second derivative change? If it changed, we're golden. If it didn't change, not golden. So again, this is concave up because the second derivative would be greater than 0. And this would be concave down because the second derivative would be less than 0. Let's just write that back in there again. So this is concave up right here. And this would be concave down. All right, so all of a sudden we have our function, and we have these different layers of functions. The first derivative tells us when a graph is increasing or decreasing. And the second derivative tells us if it's concave up or concave down. And they give us different things. So for us, we want to remember certain things about what's going on here. And we're going to just focus on the second derivative. Tomorrow, we're going to spend another day just kind of tying this all up tomorrow. And we'll deal with first and second derivative at the same time at that point. So point of inflections occur when the graph changes concavity. Or points of inflection occur when the second derivative changes signs. We don't care how it changes, as long as it does change. But big idea, remember, just like with relative extrema, points of inflection, they exist at critical numbers of the second derivative. I should probably write that before I get to the big thing. So actually critical numbers of the first derivative, because critical numbers are when the first derivative is 0, so critical numbers. But these are going to be more critical numbers for our second derivative. So points of inflection don't always occur when the second derivative is a critical number. Just like we didn't have a relative extrema always when the first derivative was a critical number. The first derivative must change sign. The second derivative must change signs. Yep. And that's going to be kind of this idea that we're dealing with here. It has to change signs. If it doesn't change signs, we don't have ourselves a critical number. So let's take a look at some here. We actually know now quite a bit about these graphs. Let me draw something for you. We'll call this one f of x. Like that. There's f of x. I don't know why I put an apostrophe there. There you go. But now I want you to think about what happens at f of x. For these values here, those are our relative extrema. And that's relative extrema, that's when our first derivative is equal to 0. If our first derivative is a positive number, that means the graph's increasing. Notice this increases, so I have a derivative that's a positive number. Graph decreases here, so I have a negative number. Increases here, so I have a positive number. There's my graph, my first derivative. And then, here's my point of inflection in here. Notice the point of inflection is the relative min or max of the first derivative. So my relative max goes here. Since it's concave down to begin with, that means I have a second derivative that's negative. It's concave up, so my second derivative it goes to be positive. This is my graph of my second derivative. And you can start to see how all these things are related, how the graph of the first derivative and the second derivative are related to the original graph. And we can start to see when you'd have x-intercepts on your first and second derivative based on your graph. When your graph's going to be increasing and decreasing. And notice, we went from a cubic for the regular function to a quadratic for the derivative to a line for my second derivative. It always goes down by a degree every time we take a derivative. Just think of the power rule. So what we're going to do today is we're going to just play a little bit more with it, some of the functions we began to play with yesterday. A little bit more. So the second derivative exists, or points of inflection exists when the second derivative changes signs. Yeah. So if it doesn't change signs, no point of inflection. Determine the concavity for f of x equals 2x cubed. I should make this black actually. 2x cubed minus 3x squared minus 12x plus 1. And again, if you look at it, we dealt with this function yesterday, right? Determine the points of inflection for f of x. So cubed. So since we dealt with this yesterday, I want us to remember a little bit about what's going on here. Okay, I'm going to come back and I'm going to draw some of the things that we saw yesterday. Just want you to see it a little bit. Yesterday when we did this problem, we said it had a relative minimum at 1, negative, oops, a relative max at 1, negative 8. So in other words, or negative 1, 8, I'm sorry. Right about there. And then I had a relative minimum at 2, negative 19. So when we looked at this cubic, we found the relative max, and you guys can go back and check the video and check your notes to see that. And then we had this relative minimum way down here, and then it came back up. Well, at some point in time, what we should find out when we look at this is there's going to be a point where our graph goes from facing downward to facing upward. So I should have a portion that is going to be concave down. I should have a portion that is concave up. So that's going to be kind of what we're hoping to see here today. Okay. So just so you're aware, this is what we're kind of hoping to see. So we said yesterday we had this at, that was at negative 1, 8. And this was at 2, negative 19. So again, that's what we saw on the last video. All right, here we go. And once again, we're going to say what we're going to do. We're going to do the work. When we're done, we're going to say what we found. All right. So f of x is concave up when the second derivative is greater than 0, and concave down when the second derivative is less than 0. Points of inflection will exist when the second derivative changes signs. All right, so we said what we're going to do. We're going to be playing with concavity. We're going to be playing with this idea. I can get that up there a little bit. See here? Oops, maybe not. Maybe I can, maybe I can't. There we are. So concavity exists when the second derivative changes signs, and it's concave up when it's a positive derivative, concave down when it's a negative derivative. We gave ourselves permission. We said what we're going to do. Now we're going to turn around and we are going to do the work. So I've given myself permission that I need to go take a look at the second derivative. So first up, get my first derivative, and again, this go back to your notes, you'll see the same derivative yesterday. We had 6x squared. It's a series of power rules. Minus 6x minus 12. Now I'm going to do my second derivative. I get 12x minus 6. It would be good if I probably include the x there. All right. So I gave myself permission to get to the second derivative. I said I want to talk about it being equal to 0. So I'm dealing with a second derivative value at x. And just like with yesterday when we were dealing with the number line, we're going to be doing the same type of idea with the number line to be able to test my second derivative now instead of my first derivative. Okay, so we're going to test it. So I'm looking at any value from negative infinity, any value from negative infinity to 1/2. So how about we just go second, we'll test the second derivative when x equals 0. That's an easy one. As well as we're going to test the second derivative when x equals 1. So we're going to test our ranges to see is our derivative a positive value or a negative value. When I plug 0 into my second derivative, I get negative 6. So that means my second derivatives in this region are less than 0. And by the way, that means it's concave down, and you can see how it opens down. When I plug in 1, I get a second derivative equal to 6. That means my second derivative is greater than 0 in this region. That means it's going to be concave up at the end, and you can also see how it's concave up. That means that I have a point of inflection at 1/2. So I need to figure out what that value is at 1/2. So if I plug it in there, when I go and I plug 1/2 back into my original function, going back to the original function now again, I'm going to end up with a negative 11 halves, or negative 5 1/2. All right, so we said we're going to do. We did the work. So when we're done, we're going to say what we found. F of x is concave up, or concave down, from negative infinity to 1/2. I'll have to write those in here in a second. Because f double prime of x is less than 0. F of x is concave up from 1/2 to positive infinity because second derivative is greater than 0. Negative infinity to. All right, and then we also had a point of inflection. Point of inflection exists at, and I'm going to go back and write all these points in there for you in a second. Because second derivative changes signs at x equals. Now notice, as I go through and write all my fractions in there or whatnot. So I have negative infinity to 1/2 is where it is concave down because the second derivative is less than 0 from negative infinity to 1/2. From 1/2 to positive infinity, it's concave up because the second derivative is greater than 0 from 1/2 to positive infinity. And I had a point of inflection at 1/2 negative 11 halves because the second derivative changes signs at x equals 1/2. But notice, I didn't have to say how it changed signs. I can, but there's no reason to. All I need is it to change signs. I don't have to specify how it changed signs. So now, if I were to go back to my graph and I throw in some of these things here, I know where that point of inflection existed. So 1/2 negative 11 halves. And it kind of makes sense that that happened there. I know that on this region here, this is when my second derivative was less than 0 because it opened down. And I know that because this opens up here, that means my second derivative here had to be greater than 0 because it was concave up. And you can start to see now how all the pieces kind of come together. Right? And I could have gone back here if I wanted to and added my first derivatives in here. You could start to see how this whole function can be described by first and second derivatives. I can get a real good idea what happens at for this graph. I get to know a lot of stuff. All right, but anyways, back to our work here. And again, remember what we did here. We said what we're going to do. We did the work. And when we're done, we say what we did. Okay. So let's have you guys try one, shall we? Let's have you guys try one. I want you to determine the points of inflection for f of x equals 3x to the 5th minus 20x to the 3rd plus 2. So why don't you guys, let's see, I'm going to write this up here for you. Whoop. All righty, and why don't you guys go ahead and pause the video now and give this problem a shot. Go for it. All righty, let's try this here. By the way, again, this is another one that we've done before already, right? And we found out on this one, when we did this one yesterday, we had a relative max. And that's a weird way to spell relative max. There we go. At, I was at negative 266. We had a relative minimum at 2, negative 62. And no relative extrema when x equaled 0. Even though it was a critical number, our first derivative didn't change signs there, so nothing happened there. So just a little bit of a refresher course. All right, so that's what we saw yesterday when we dealt with this problem. What are we going to see today? Points of inflection can or will occur when the second derivative changes signs. This can happen when the second derivative equals 0 or when the second derivative is undefined. All right, so we gave ourselves permission. We're going to be playing with the second derivative. So we said what we're going to do. Now we're going to do the work. So f prime of x equals, we saw this yesterday, was 15x to the 4th minus 60x to the 3rd. And then we had a second derivative then. If we were to keep going on this, we had to have a second derivative on 60x cubed minus, that should have been a 2 back there, friends. There we are. minus 120x. So we found the second derivative. We're going to set it equal to 0. Ooh, it is getting really smoky outside, friends. I'm not going to lie. I probably should go home here to get out of the smoke because the smoke likes to seep into this room. All right, so we're going to go ahead and take our derivatives here. X squared minus 2. So that means I'm going to have 60x. I have x minus root 2 and x plus root 2. So I'm going to have 3 critical numbers to my second derivative. So those are the values that I'm going to find. All right, what does our second derivative do at these values? So we're going to put them on our number line, and we're going to test the intervals. So from negative infinity to negative root 2, I need to pick a value to test. How about x equals negative 2? Between negative root 2 and 0, we can test it with test negative 1. We're just testing values in between these intervals from 0 to root 2 and from root 2 to positive infinity. I'm just going to plug them into my second derivative to see what the second derivative does on those intervals. So if I plug negative 2 in there, I'm going to get a negative and negative and negative. Looks like I'm going to get a second derivative that is less than 0. I plug this one in there, I'll get a second derivative that's positive than 0. Plug this one in, less than 0. Now plug this one in, get one that is greater than 0. So what happened? They changed signs here, so therefore I had a point of inflection. The second derivatives changed signs here, therefore I had a point of inflection. And by the way, remember, we didn't have a relative extrema when x equals 0. Didn't change directions for the first derivative. Well, the reason for that is it wasn't a relative extrema. It turned out it was a point of inflection. And then our last one we had went from less than to greater than, changed signs again, so I have another point of inflection. So if I plug these into my calculator here and try to figure out some values here, it turns out I have a point of inflection then when f of 2, or negative root 2, when I plug that in, whoop, and I'm sure you guys are probably doing this one in your head, and you probably came up with negative 28 root 2. Yeah, I'm just playing. Plus 2. If you want a decimal, I can give you a decimal. That's about negative 37.598. When I plug in this one, f of 0, what I can do real quick, that's 2. And when I plug in this one right here, the positive root. Oops, I got the wrong value for that one. Excuse me. Got the wrong value. Should have been a positive. Hard to get that here. Couldn't read my own handwriting. I maybe calculated these earlier. So that was 41.5988. All right, and when I plugged in a positive root 2 in, I'm going to end up with a negative 28 root 2 plus 2. which is about negative 37.598. All right, so what all does that mean? We said we're going to do, we did the work, now we're going to say what we found. Points of inflection exist at negative root 2, comma, 41.598, 0, 2, and root 2, comma, negative 37.598, because the second derivative changes signs at x equals negative root 2, x equals 0, and x equals root 2. And I need to put those in there real quick. Got to get some radicals going on. Whoop, 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 and whoop. All right, you're used to me saying it by now. Say what you're going to do. And then you do the work. And when you're done, say what you found. And notice, friends, and again, even though we already said it, when x equals 0, even though that was a critical number the first time we did it on the first derivative, wasn't a relative extrema. But since something critical happened there, shouldn't be a big surprise that it was a point of inflection. It was a critical, because it was a critical number again for the second derivative. All right, let's try one more here just to really make sure we have this down. I'm pretty sure you got a pretty good idea what equation I'm going to pick here. From 0 to 2 pi, to determine the points of inflection, to f of x equals negative 2 sine of x plus 1. All right, go ahead and pause the video, and then we'll take a look at it here and call it a day. All righty, let's see what we're gonna do here. Again, by now, you guys are more than know what I'm gonna say, I'm sure. Say what we're gonna do. We're gonna do the work, and when we're done, we're gonna say what we found. Points of an inflection can exist, will exist, when the second derivative changes signs. This can occur when the second derivative equals 0, or when the second derivative is undefined. All right, and again, we dealt with this one last time as well, so no big shocker. We're going to be hitting it one more time. All right, so let's see here. First derivative. I have negative 2 times cosine of x. Now we're going to get the second derivative. So I gave myself permission to come down to this. So negative 2 times negative sine of x. So negative times negative makes that a positive. So 2 sine of x. There's my second derivative. And then I'm going to go ahead and plug in 0 for my second derivative. So we have 0 equals sine of x. And again, we're thinking about the unit circle. Sine is when my graph, my y value is 0. So that's going to be here at 0, pi, and 2 pi. So that means x equals 0, x equals pi, and x equals 2 pi. But one big thing to remember for this is, friends, I'm not including 0 or 2 pi. I'm only including what's between 0 and 2 pi. That means I get to toss out this one and that one. They will be gone. They don't fall in my domain. I only got one number I got to check. So let's check it. I'm looking for a number between 0 and pi. How about, let's go with pi over 2. And one number between pi and 2 pi, let's go with 3 pi over 2. Just like that. If I plug it in, pi over 2, sine of pi over 2 is 1 times 2 is 2. That's a positive number, friends. I have a second derivative that is greater than 0. I plug 3 pi over 2 in. Sine times 3 pi over 2 is negative 1 times 2 would be negative 2. I have a second derivative that's less than 0. They do change signs, therefore I do have a point of inflection. Okay. So again, they do change signs. So therefore this is a point of inflection. So now I've got to go and plug pi into my original equation to figure out what that point of inflection is. Because again, a point of inflection is a location. So it needs to be a point. If I plug in there, sine of pi is 0 times negative 2 is 0 plus 1 is 1. So we said what we're going to do. We did the work. And when we're done, we're going to say what we found. So point of inflection exists at pi, comma 1, because f double prime of x changes signs at x equals pi. And one more time, because we cannot say it enough, say what we're going to do the work, and when we're done, we say what we did. All right, friends. So tomorrow, we're going to go one more step, and we're going to tie everything all together. We're going to have one more day with relative extrema and points of inflection and increasing and decreasing, concave up, concave down. We're going to tie it all together. Plus, we're going to look at one other thing called the second derivative. So I'll see you guys tomorrow. Take care.